Hi, I'm Austin Westbrook, and this is Lab 5. The purpose of my lab is to analyze the motion of a falling slinky and relate it to a computational model. The motion of the slinky is interesting as the bottom remains stationary until the spring is no longer stretched, as we will see throughout the presentation. The main ideas and equations is the energy principle, Newton's second law, especially the position and velocity update formulas, spring force, and spring energy. And our equations are going to be the velocity update formula, position update formula, force of a spring, potential energy of a spring, kinetic energy, and potential energy by gravity. And the result preview is that the observed model was fairly similar to the computational model. As for both models, the bottom of the spring remained at rest until the spring was at its relaxed length. This is our observed experiment. Um, as you can see, he's dropping the slinky from rest. The system is the spring and the surroundings is the earth. The initial conditions is that the spring is stretched and released from rest, and the only intended forces are the spring force and gravity. I was able to find online that the relaxed length was about 0.08 meters. The K value is about 6.5 Newton meters. The mass of the spring is 0.22 kilograms. And this was the initial position. And I tracked the motion of the bottom of the spring, as you can see here, and I calibrated the data by assuming that this person was about 6 foot. So here's the computational model. Here's all the data I needed for the spring, the L hat, and S, and then our kinetic and potential energies, and those added up give us the total energy. I was able to find that the spring took about 0.3 seconds to compress. So during that interval, we find the energy and then find the force of the spring and then the force of gravity. And in this case, the spring position is the top of the spring. So to find that position, we're going to use FNet2, which subtracts the force of the spring from gravity since they are both pulling it downward. But for the um, bottom of the spring, we use FNet because the two terms cancel out, so they're going to be added together. And then after the 0.3, then it's just the force of gravity that pulls the entire spring down. And as you can see, the models are pretty similar. It stays constant until 0.3 and then drops down. Here, it is a little bit before 0.3, so my observation could have been slightly off. Possible error, as seen in the graphs, there is a slight discrepancy between the model and observed experiment. This could be due to outside forces such as drag that were not included in the model calculations. So what causes the bottom of the slinky to remain stationary as the top falls? As seen in the code, the bottom of the slinky is affected by two forces, spring force and gravity. Although gravity is pulling it downward, the top of the slinky pulls the bottom upward, which balances the forces until the spring becomes relaxed. However, for the top of the spring, both gravity and spring force are pulling it downward, so it goes downward the entire time. Thank you.